Assalamualaikum warahmatullahi wabarakatuh. Welcome back to my video. So let us resume with work example 2.0 on SLD topic. So for the single line diagram shown below, calculate the total S apparent power. So P the active power, Q the reactive power, and currents I1 through I8. So for example, we do have this single line diagram. So we analyze at the load part or load region. We start with I1, okay, up to I2, I3, I4, I5, I6, I7, and I8. All right. So this is again the bus bar, which is having a rating of 11 kilovolt. So I believe this is the similar bus bar voltage rating. So 11 kV. So this is another 11 kV. All right. So each component over here, M1, is provided with its respective value of the S, P, the impedance, the active power, as well as the power factor. Okay. So let us analyze this example or this circuit in order to calculate the total S, P, Q, as well as the value of current I1 through I8. Okay, so let's focus on each part. We start beginning from motor M1. Okay, so again 11 kV for the bus bar. So we have I1 flowing into or heading to M1 motor number 1. So with 300 kVA, 0.8 PF lagging. Okay. So given apparent power S1 equal to 300 kVA volt ampere, so cos theta 1 0.8 lagging. So from the formula S equal to square root 3 VLIL. So rearrange in terms of I1 or IL. Okay, this is I1, or particularly in this example known as IL. So S1 equal over square root 3 VL. So substitute the value of S1 from here. This is 300 volt ampere into this equation, and take the value of VL, the line voltage, which is 11 kilovolt. Substitute into here this equation, and I1 give the value of 15.746 ampere. By the way, so we will also need to find Q1 and S1 for later use. Okay, so for this particular part, we still, even though we have done with I1 or IL over here, so but still we need to find value of Q1 and S1 for later use. Okay, so we'll see how. So now theta 1 equal to arc cos 0.8, or in degrees 36.87 degree. So where theta 1 is phase angle between V phase, the phase voltage, and phase current of load. So again, the power triangle for M1. So we do have S1, P1, and positive Q1. Why it is positive? We can clearly see from the lagging condition of the power factor. Okay, so once it is lagging, so Q1 is actually positive. Okay, lagging load Q1 is positive. This means it is heading upward. Okay, from endpoint of T. Okay, or we can easily understand from the P position, where P is lag behind S, or it is located underneath S. As this P is located underneath S or lag behind S, so the Q1 is positive. So lag king reflects the position of P1. Lag behind means Q1 is higher and thus result in Q1 is positive. Okay. So from power triangle, active power consumed by motor 1 is again from power triangle or from trigonometry relationship. So we are able to come out with this equation. So S1 cos theta 1, S1 is provided. So this give you in question. So 300 k volt ampere cos 36.87 the power factor. Alright, so here this is the value. Okay, into this equation, P1 finally give us 240 kilowatt. Okay, so what about Q1? Again, from trigonometry or from power triangle. So rearrange the equation. So again, substitute value of S1, which is 300 k volt ampere, and sine 36.87 degree. Thus, we get the value of Q1, which is 180 kilowatt. Okay. So therefore, complex power consumed by motor M1 is S1 equal to P1 plus JQ Q1. So this is the value we just obtained in the previous page, and this is from above. Okay. So now we come to second part of the analysis of all the region of the load area, which is the position of M2. So the motor 2, we have the active power 200 kilowatt with 0.8 power factor leading. So we have the line current over here, or the load current over here, I2, as well as the line voltage, the bus bar line voltage, which is 11 kilovolt. So given active power P2 200 kilowatts, right, and then cos theta 0.8 leading. So from the formula, P equal to square root 3 VLIL. Again, this line current, this is actually equal to I2, or I can simply write that I2 is equal to IL. So I2 equal to P2 over square root 3 VL cos theta. So this is 400 kilowatt from this question again here. And then this is 11 kV, the line voltage from the bus bar. Then this is again the power factor. And now I2 equal to 13.12 ampere. Okay, so we have done with I line for the second motor, or I2. So again, we still need to find Q2 and S2 for later use. So now theta 2 is equal to cos 0.8. So this is from 0.8 power factor over here. So in terms of radian, now we have the value in degree, which is 36.87 a degree, where theta 2 is a phase angle between V phase and I phase of load. Again, referring to power triangle of M2. So now we have over here negative Q2. So negative is coming from the leading load. Alright, it's a leading power factor, leading load. You can see from here, this is leading. Okay, leading, and this is leading, and make sure once the power factor of the load is leading, this means the Q is negative. Or we can simply refer to P. Leading means you refer to P. So this is how you can understand, how you can draw the power triangle. So once it is leading, means P2 is leading S2, or we can, in common, P2 is leading, P is leading S. Alright, so on top of S, okay, P is located on top of S, meaning P2 is, E2 is leading. Okay? Or we can simply understand from the position of Q2. Leading means negative. as well. So this is the value of degree 36.87 between P2 and S2 with negative Q2. So then from power triangle, reactive power consumed by motor M2 is Q2 equal to negative P2 tangent theta 2. So don't forget the signage, the negative symbol or negative sign. So 200 from question, substitute directly into this equation, and then tangent 36.87 from here, all right? So into here, okay, and then we'll finally determine the value of Q2, which is minus 150 kilowatt. So next step is to calculate S S2. We don't need to calculate, we just collect from previous analysis. S2 equal to P2 plus JQ2 and put into this equation from 200 kilowatt and minus 100 J 150 kilowatt from here, all right, and from here the question P. And then what happened when we come to the third part, or I3 consists of cable 3. So total power complex supplied by cable 3 is S3 equal to S1 plus S2. So this is the reason why we calculate S1 and S2 in the beginning of the solution. Okay, because when we arrive at cable 3, okay, when the analysis arrived at cable 3, so we must calculate the total complex power of S3. How to calculate? We just sum up or total up the S1 plus S2. Alright. So S3 equal to S1 plus S2, 240 plus J 180. This is from previous page, and S2 is from here. We just calculate above, all right, the value of S2 into this S, and then finally we can obtain the value of S3 440 plus G 30 k volt ampere, right? So next, after we calculate S3, we try to plot the again power triangle for cable 3. So we do have S3, P3 and Q3. How can we know again the Q is at this position? We can simply say this is positive. So how can we know? So just got back to the previous slide and watch from here. Okay. So S3, this is equal to P3 again, just to recall. Okay, we have JQ3 over here. So that means the value of JQ is positive. Okay. Then when we come to power triangle, so we can simply write the positive value of Q3. Okay, it's over here. So now tangent theta 3, this is equal to Q3 over P3, Q over P, and then we can directly get the degree angle of theta 3, up tangent, Q3 over P3, substitute a value of Q3 60 from here, alright, from here. This is actually okay, this is actually wrong. This is not 60, but this is obviously 30 over here. Okay, this is 30. So this is not 60. So this is 30. I have not updated this slide, but partially I have done it, not the total improvement. So this is still same, which is 440. All right. So you should have a new value of theta 3. Instead of 60, now we have t over here. Okay. And then what happened? So using the formula of P equal to square root 3 VLIL cos theta t. So we get over here P3 over square root 3 VL cos theta 3. Okay, so substitute again. This is supposed to be a new value, okay, into here. So we got the I3, which is 23.3 ampere. All right. And then the fourth part, or part number 4, which is comprising the Z, or the impedance, the phase impedance, which is minus J1000 ohm with delta connection. Okay. And then we have again the line voltage bus bar over here having 11 kV, and therefore IRY, this is actually okay, so it's actually data connection, so we can draw out in details how it looks like. So we have R, Y, B, phase of R, Y, and V. So this is the phase value of impedance, which is Z. So as I emphasized in the beginning of this topic, so we do have only a single line over here that represent the whole three-phase system. So just assume this is from this one connection, okay, or this one part. And then IRY, so we do have IRY over here. This is how we can draw the direction or the flow of IRY. So this is VRY. So we have Y over here. Okay. So we have VRY over here over ZRY. So ZRY is the phase impedance. So this is again provided in question. Okay, so this is VRY. So we do have 11 kV. Right, so this is 11. This is 11 kV. All right, 0 degree over minus J 1000 ohm. So solving this, we can get the value of IRY. Okay, just like that. Okay, and then therefore I4, this is actually the line current. Okay, line current. So remember, for data connection, so the line current, so this is equal to square root 3 I phase. All right. So I phase in this particular example is actually IRY. Okay, this IRY, okay, the one I circle is here, and all these are in phase mode. And we can say that IRY, this is actually the phase current, and comes to I4, so we need to convert into I line or line current multiplied by square root 3. Okay, so 11 multiplied by square root 3, so the I line or I4 is now 19.05 ampere. So what about the complex power consumed by the rate phase impedance? Since we are analyzing one phase, namely I4 or IL over here, so we can calculate only the rate, for example, rate phase. So we have seen here, this is the rate phase over here, R2Y. So the rate phase over here, okay, only this phase. Okay. And then we can simply write that the complex power consumed by rate phase impedance of capacitor bank number 4 is as RY. This is the equation V RY I RY conjugate. Okay. So substitute again the value of RY. So VRY is 11 kV. Here is 11 kV over here. Okay, or over here. Okay, and then multiply by I RY. We just obtain over here. This is I RY. Okay, so remember the symbol conjugate. So now we have negative value. Okay, and then the complex power of rate phase impedance, for example, is equal to 1 to 1 negative 90 degree. So therefore, the total consumed by the total complex power consumed by capacitor bank number 4 is just multiply with 3. All right. So this is, since this is red phase only or single phase only, so when it comes to complex power consumed by capacitor bank, this means we need to calculate in 3 phase. Okay, just multiply by 3, this value multiply by 3. Okay, to get value of S4. This is equal to S4. Okay, the total complex power 363 minus 19 degree kilovolt ampere. Right. And then again, load number 5, so 11 kV, the line voltage with the bus bar voltage. So we have I5, the line current at load number 5 with Y connection of load, and impedance, the phase impedance is 1093 degree ohm. So given ZPS, so this is a negative J 1000 ohm. So therefore IRN equal to VRN over ZRN. So remember, when it comes to star configuration, so the V phase, okay, so this is equal to V line over square root 3. Okay. So by having that, once we come to analysis, IRN, okay, equal to VRN. So this is the phase value. This is the phase value. So we should have V line divided by square root 3. V line in this example is 11 kV. Okay, so 11 kV divided by square root 3 to convert it into phase value VRN. Okay, this phase value according to this relationship, and then divided by the Z value. So here, for example, so this is minus, so this is the point of N. Okay, this is the point of N. So this is R Y B again. Okay, so DI5, this is equal to I and for here, for example, so this is VRN. Okay, we have V, this point N, so we have VRN over here again. Okay, this is point N, so we have over here VRN, and then we have Z VRN over ZPH, so minus J 1000 ohm, so we simply get the value of J 6.35 ampere. So once you convert to polarity, so we can calculate, or we can get the value of I5, which is 6.35 ampere. Okay, so take the positive value of there's modulus over here, so the actual value, okay, the magnitude, so which is 6.35 ampere. So complex power consumed by rate phase impedance of load number 5 again. So refer to this power triangle. How to draw? Again, you may refer to the Q5 over here. So this is actually 90 degree apart, and then so you can simply calculate that the value of S is 90 degree here. Okay, this is this is actually coming out after we calculate this equation. Okay, again, for the total for the single line of complex power, the rate phase impedance, for example, okay, VRN multiplied by IRN conjugate. So Rn, the phase value, so we have the line voltage divided by square root 3. So multiplied by IRN conjugate. So this is the IRN. So conjugate, you should put minus J, or from here IRN. So this is positive. So you put it here, negative J. Now we have negative J due to this conjugate value. Okay, so now we have negative. So this is the final. So this is the final answer. All right. And then therefore total complex power consumed by load number 5 is S5 equal to 3. Again, you have to multiply by 3, okay, to get the actual or to get the total complex power from this value. Okay, multiply by 3 to get S5. Okay, so we can finally get 120.9 minus 90 degree kVA. Okay, and then the motor number 6, 400 kilowatt is provided, 0.707 lagging power factor. So this is I6 with line voltage of 11 kV. So from the formula of P equal to square root 3 VLI cos theta, we get I6. This is also referred as I6. So we get P6 over square root 3 VL cos theta. So again, substitute the value of 400 into here and the 0.707 into here. And then finally we get the value of I6, 29.6, sorry, 29.7 ampere. So now cos theta, theta 6 in terms of degree, we have 45 degrees. So where the theta 6 is the phase angle between phase voltage and phase current of motor 6 M6. Power triangle for M6 again, so you have to be careful with Q. Q is positive for inductive or lagging load. Okay, this is lagging load. So make sure the Q is positive. Lagging mean Q or P is located underneath S6. Okay. So P underneath S means Q is positive. Alright. And then put in the value of theta 6, which is 45 degree, into this power triangle. Okay, this is theta 6. And then the relationship for this power triangle in terms of tangent theta 6. So we have Q6 equal to P6 multiplied by tangent theta 6 for 100 kilowatt from the question. So tangent 45 over here, 45 over here into here, and then finally we get the value of Q6, which is a reactive power consumed by motor. So therefore, from value of P is provided in question 400 kilowatt. Q we just calculate over here 400. The combination between P and Q. So we are able to simulate or come up with S6 value. Okay, the complex power consumed by motor 6. So what about cable number 7? So cable number 7 is connected to the bus bar consisting of I5 and I6. From there, we can simply say that the total complex power of S7, this is equal to S5 plus S6. Okay, so from here, S7 equal to S5 plus S6, which I believe we have obtained earlier. So this is S6 over here, all right, so as well as S6 over here. Okay, so just total up to get the value of S7. Okay, so again for power triangle for cable number 7, so we have S, P, and Q. So tangent of theta Q, we try to obtain from this equation. We have Q and P. All right, again we have Q and P. From this Q and P with this power triangle, so we can calculate the angle theta 7. So just take the value of Q and P of S7. Okay, so from there again you use this equation. You just utilize this equation, P equal to square root 3 VLI cos theta. So we get P7, I7, right, as well as VL and theta L. Theta 7, sorry. 400 is the P value, this P value. Okay, this is cos 34.9. From here, the new theta we calculate earlier, and then this give us I7 is equal to 25.6 ampere. Similarly for cable number 8. Alright, so cable number 8 consisting S8. Okay, this is equal to S3 plus here S4, the total complex power of S4 plus total complex power S7. Alright, since it is connected to the same bus bar of 11 kV over here. So then just take the value of S3, S4, S7 into this equation and generate the value of S8. Okay, which is 840 minus J40 54 kilo volt ampere. So power triangle, so this is negative JQ or Q8, so this is P8, all right. Okay, this is JQ8, and then this value of Q8 is negative. So this is negative. Okay. So we have Q8 is negative for leading phase angle. So you can actually understand from the power triangle, or you can understand from the sign of negative over here. Okay. So now tangent theta 8 equal to Q8 over P8. So tangent, arctangent, get a new degree, which is 3.68. Okay, again into this equation, so I8 equal to P8 over square root 3 VL cos theta 8. So 880 from here into here. Okay, the new theta here into here, as well as the line voltage, which is the rating voltage at the bus bar, operate at 11 kV. So now the current I8, or the line current of I8, is 44.18 ampere. All right. So work example 3.0, sorry. So we will continue in the following voltage. Again, thank you for watching. See you in my next video.